Hi, everyone. Today's topic is text analysis in computational social science, and this is going to be your first project. This is going to be a very extensive project. We're going to code quite a lot. What I only expect from you is to replicate my coding. So just follow what I do and do exactly the same things that I do. But we have people in our class that are seeking to use text analysis for their thesis or projects. And to that extent, I think I have to explain to you how we do text analysis in computational social science before actually starting the coding session. So when we say computational text analysis, there are different other ways of calling it, such as quantitative text analysis, automated content analysis, text mining, text as data, and so on. So these all connect to natural language processing and machine learning, and this is developed in order to read very large quantities of text. So a constitution, for example, an extremely large document, or the entire legal system or entire legal documents of a country, diplomatic documents for the last 200 years. So computational text analysis is never as detailed as manual human reading, but it is an acceptable form of analysis when the text size we're dealing with is just so large that it is impossible for a person to read all of that. And from this, we have a new scientific discipline called natural language processing, which is actually a field of computer science and computational linguistics. It is concerned by making computers understand text and spoken words in much the same way human beings can. So when you use ChatGPT, for example, the algorithm there learns from statistical learning. So it reads extremely large quantities of documents and text and assigns statistical values on keywords or words that have a high likelihood of appearing next to each other. And through this statistical understanding, this statistical measurement, we have computer language and the field of natural language processing. And it's basically a way for us to speak to computers and for computers to be able to speak to us in a way that we understand. And this language, this computational linguistics problem is actually a very old problem. It's as old as computers themselves. Originally, computers basically only understand binary data, so 0, 1, 1, 1, 0, 1, 0. Then over the 1960s, 1970s, a new octal system was used for engineers to program, for code, to configure machines. Then hex programming language was developed, and in the 1980s and 1990s, ASCII values were being used. For those of you who are old enough, maybe before the invention of Windows operating systems, we used DOS operating systems, and DOS relied excessively on ASCII values. Now, there are two main phases to natural language processing: data pre-processing and algorithm development. For you to be able to do textual analysis, you first have to prepare the text for analysis. And the first thing you always do is what we call tokenization. A token is a quantified version of a text. So when you have a sentence like this: grew a pretty little fir tree, and yet it was not happy, rejoice with us. The tokenized version of this is basically every single sentence, every single word identified as a single token. and the capitalization is gone. They're all lowercase letters. The punctuation is gone. You don't have any punctuation. So you just have words in lowercase format. Taking a text and breaking it down into individual words is called tokenization. Then the second aspect of data pre-processing is called stop word removal. Stop words are common words that appear very frequently. So and, of, the, in, on. These are all stop words, maybe unnecessary words that do not contribute to the meaning of a text. So you do stop word removal because when you count the occurrence of certain words in a large body of text, the most frequent terms you're going to come up with are going to be stop words: a, and, the, in, on, off, from, to. So when you remove these stop words, you are left with the actual relevant and important terms in a text. Then we do lemmatization and stemming. This is when words are reduced to their root forms of process. So basically going, gone, they always stem to the root of go. Changing, changed, change, they all have the same single root and the stem of change without E. So you basically reduce all words to their basic form. So Jenna went back to university. You normalize, you convert capital letters to lowercase letters. So it becomes lowercase Jenna went back to university. Then you tokenize Jenna and went and back and to and university. Then you remove the stop words. In this context, back and to are redundant words. So you only have Jenna went university. And then you stem and lemmatize. Jenna is Jenna, but went is stemmed and lemmatized back to its original form, which is go. And university, universe, universities, universes. So it has to be reduced to a stem of the universe. Then you do part of speech tagging. This is when words are marked based on their part of speech, such as nouns, verbs, and adjectives. So you specifically identify this keyword is a verb, this keyword is an adjective, this word is a noun. So this is a basic example of a word cloud for a climate change related text. So you have emissions, action, global, but you see that the most frequent terms are the, and, to, in, of, by. These are all stop words. These have to be removed so that I understand the actual frequency of the words that are important, such as climate, warming, agreement, global, greenhouse. In R format, when you do frequency analysis of certain words in a Twitter text, for example, this is usually the top most frequently occurring words: the, to, and, of. Most of the time there are links, HTTPS, t.co, which is twitter.com in short format, a, in, is, for. When we do data pre-processing or data cleaning, we always have to get rid of these stop words. These are all called stop words. And then we stem, connect, connected, connection, connections, connects. They're all stemmed back to their original connect. Trouble, troubled, troubles, troublesome. They are all stemmed back to trouble, trouble, trouble, but troublesome can also be stemmed to trouble, but also troublesome. Then we do actual analysis. There are multiple ways of doing computational text analysis. One, keyword analysis, where you look for certain keywords, certain key phrases, and maybe count them, maybe count how many times they appear in a text. You do named entity recognition, which extracts and categorizes a text's corpus, proper nouns, and other information types. So in this context, a keyword analysis is SEO. So keyword analysis goes to a text and counts the occurrence of SEO, SEO, SEO, SEO, and gives you a frequency analysis of how frequent they appear in a text. Sentiment analysis, it quantitatively determines effective trends in a document or corpus. You do sentiment analysis through libraries or dictionaries. Libraries and dictionaries are pre-arranged or readily available databases in which you identify whether a word is a positive or negative beforehand. So in this context, when you are text analyzing a review for a product, awesome, incredible, brilliant, these are all positive sentiment words. But for a computer to automatically understand that these words are positive, you have to have a pre-trained classifier or a certain dictionary so that the computer assesses quantitatively and statistically to determine whether that is, negative, very negative, positive, very positive, or neutral. You can do stylometric analysis, which is the use of quantitative and statistical methods to determine literary style. So the computer reads a text and tries to understand whether that text is a legal document, whether it is a sales document, whether it's poetry, whether it's a novel. For it to be able to understand this, of course, it also needs a pre-trained model of thousands and thousands of poems, thousands and thousands of legal documents, so that it can quantitatively and statistically understand the style of the text. Then we have topic modeling. Topic modeling determines the thematic composition and aboutness of a document or document in a corpus. So in this context, the ISIS has claimed responsibility for a suicide bomb blast in Tunisian capital earlier this week. This is basically looking at this text and try to identify the organization name, the location name, dates, phrases, person-related phrases, weapon-related phrases automatically on its own. And then it counts the occurrence of certain keywords next to each other and produces another statistical model, which says, for example, that ISIS, Amaq news agency, militant group, they all belong to the topic called organization. Whereas Tunisian or Tunis, it has a high likelihood of being statistically counted as a location. So as you can see, quantitative text analysis is heavily reliant on statistics. And the majority of the measurements and definitions and concepts are very dependent on statistical analysis. Now, before we go into further detail, I'd like you to be more familiar with UTF-8, UCS Transformation Format 8. So every digital text is encoded. It is encoded in Chinese, in Japanese, in Latin, in Arabic, in Farsi. So for different languages to be encoded in such a way that they can be readable for the majority of computers in the world, they need a universal and generalized format. Now, in the past, the most popular encoding formats were the ASCII or ISO 8859. These were different ways of encoding machine text for computers to understand, for humans to understand. And as you can see, throughout up until mid 2000s, ASCII used to be the dominant encoding format of the web. In 2005, UTF-8 was designed so that ASCII codes, hex codes, octal codes, Latin script, Chinese script, Cyrillic alphabet, Farsi script, they all can be used interchangeably and in such a way that machines can understand it. It was invented very recently, and since then became the dominant encoding format on the web. Now, sometimes on Excel or R or Python, you see garbled texts like this. When a text is garbled, it means that your computer cannot understand the encoding format of the text. So most likely that text is encoded in a different format, and your computer has no idea what format it is encoded, so that it cannot decrypt its codes into actual letters that you can read. This is a UTF encoding error. In order to prevent this from happening, always encode your text in UTF-8 and always use text that is already encoded in UTF-8. Most of the text errors that you get on computers, again, on Excel, R, Stata, or Python, is because of this UTF-8 encoding problem. When texts are not encoded with UTF-8, they produce garbled text like this. So another concept that I need to explain to you is n-grams, unigram, bigram, trigram. So let's say this is Big Data AI book. Unigram gives you single word or single characters. Bigram gives you, dual characters or dual keywords, and trigram gives you, 3 characters or 3 letters. This is important because when you are doing text extraction in large-scale text, sometimes you are looking for the stemmed version of a certain text. So let's assume that you are looking for a keyword that contains values such as change, changing, changed. You code your algorithm in such a way that it looks for a combination of 5 characters, which is C, H, A, and G, change. And you basically look for the n-gram of that specific text. So the same goes for the combination of keywords. So when you are looking for a drone strike, for example, you have to look for the bigram that contains both drone and strike. So if you do not look for the bigram of it, you're going to get results that only contain drone or only contain strike. But when you're specifically looking for a drone strike bigram, you have to look for them in such a way. So unigram, bigram, trigram, these are all hugely important when you're doing text extraction or information retrieval. The best book, I would say, on this, which exists today, is a new incredible book called Text as Data, a new framework for machine learning and the social sciences. It's written by Justin Grimmer, Margaret Roberts, and Brandon Stewart, 3 of the top scholars in this field. It explains some of the most novel methods in text analysis and computational text analysis, and how it's used in social sciences, such as political science and international relations. It's out from Princeton University Press, and it's also in our library here at Özyeğin. So if you're interested in text analysis methods, this is the book that you have to pick. Now, let's talk a little bit on the analysis. As I mentioned, text analysis is very technical, and it is also very statistical. So we're going to progress deeper into the field of counting and statistics. And the first stop that we have is the bag of words model. So it turns a text into fixed length vectors by counting how many times each word appears. So this process is often referred to as vectorization. So first you have to tokenize a text, and then you have to vectorize the text. So let's say we want to vectorize the following: the cat sat in the hat, the cat with the hat. So these are all, each single small phrase is called a document. So we are counting the occurrence of each word, each keyword in that document. So we only have, when we tokenize this text, we have the cat sat in the hat with. These are the top keywords that we have in all these three documents. Then we vectorize this. So we add the documents, the cat sat in the hat, and so on. The vectorization of the first example is that on the columns, we have different individual documents, and then these are vectorized keywords. So in the cat sat, we have one occurrence of the, one occurrence of cat, one occurrence of sat. We do not have any occurrence of in, hat, or with. The cat sat in the hat document contains two occurrences of the, because it has two thes: one cat, one sat, one in, one and hat, one with. The last one, the cat with the hat, contains two occurrences of the, one occurrence of cat, zero occurrence of sat and in. So this is essentially how you vectorize this. And the vectorized version of the tokenized form of your text is called a document term matrix. It matches each document with the terms that are included in it or not included in it. So now we have a length 6 vectors for each document. So the cat sat vector is 111000. The cat sat in the hat has a vector of 211110. So this is essentially how you do the bag of words approach, and then you do statistical analysis with this. So are you going to be on campus anytime tomorrow? Let me know if you want to have a meeting tomorrow afternoon. So this is basically the tokenized version of every single keyword that appears here. And this is the vectorized form of counting their occurrence in the general text. Now, we are going to get even more complicated by using TFIDF. TFIDF is a very popular computational linguistics term, and it's actually a function. It's a mathematical function. And it is a little bit complicated to explain what TF-IDF is, but it is an extremely useful text analysis method. So TF-IDF is the short form of term frequency inverse document frequency. It can be defined as the calculation of how relevant a word in a series or a corpus is to a text. Now, there are different documents, means that, let's say you are studying parliamentary debates. A parliamentary debate on day 1 is one document. Parliamentary debate 2 on day 2 is the second document. Parliamentary debate on day 3 is the third document. So each date is your document. So you are looking at how frequent certain terms are in each document and calculate the frequency of their occurrence in an inverse fashion. So in order to understand TF-IDF, first thing you need to understand is what a term frequency is. In document D, the frequency represents the number of instances of a given word T. So we can see that it becomes more relevant when a word appears in the text, which is rational. So term frequency, if a single word appears very frequently in a document, its term frequency increases. But the problem is, such frequent terms can be also stop words, such as the, a, an, or, in, of. So that's why we also have to calculate document frequency. This tests the meaning of the text, which is very similar to term frequency in the whole corpus collection. The only difference is that in document D, term frequency is the frequency counter for a term T, while document frequency is the number of occurrences in the document set N of the term T. In other words, the number of papers in which the word is present is document frequency. So term frequency is how many times a word appears in a corpus, and a corpus is the absolute collection of your text data. Now, document frequency is that maybe a term appears 100 times in the broader corpus, but if that keyword appears in a small number of documents and not all documents, it is going to have a low document frequency. It means that that keyword is only important for some documents and not others. This is why we also calculate inverse document frequency. Mainly, it tests how relevant the word is. The key aim of inverse document frequency is to locate the appropriate records that fit the demand. Since term frequency considers all terms equally significant, it is therefore not only possible to use the term frequencies to measure the weight of the term of the paper. So you also have to do inverse document frequency. So TF-IDF is a mathematical formula in which term frequency is number of times a word X appears in a document divided by number of words present in a document, and then inverse document frequency, which takes the logarithm of the number of documents present in a corpus divided by the number of documents where word X has appeared. So TF-IDF is the multiplication of the TF function and the IDF function. Now, what is the purpose of TF-IDF? The intuition behind TF-IDF is that if a word occurs multiple times in a document, we should boost its relevance, as it should be more meaningful than other words that appear fewer times. But if a word occurs many times in a document, but also along many other documents, maybe it's because this word is just a frequent word, not because it has relevant or meaningful in terms of inverse document frequency. So relevant words are not necessarily the most frequent words, since stop words like the, of, or a tend to occur very often in such documents. So let's say you are looking for a text analysis of how artificial intelligence technologies are considered as a national security problem in Turkish strategic documents. Now, when you do simple term frequency analysis, you are going to see a lot of Turkish, or Turk in those calculations. That is not what you want, because the occurrence of Turkey is not your research question. You're interested in artificial intelligence technologies and how they are defined by Turkey. So you need to conduct TF-IDF because it weighs words based on relevance. And one can use this technique to determine that the words with the highest relevance are the most important. This can be used to help summarize articles more efficiently, or simply determines keywords for a document. So just as in previous document term matrix, we have terms, we have 3 different reviews of a certain movie, for example. So every word is calculated as inverse document frequency, and then this feeds into TF-IDF calculation of the first review, TF-IDF calculation of the second review based on each individual letter. So the same thing goes for food podcasts, cake podcasts. When you are looking for the occurrence or popularity of different forms of content in social media, you basically look at the frequency of terms in relation to the documents in which they appear. Now, let's get even more advanced by topic models and LDA. Now, topic modeling is a type of statistical modeling for discovering the abstract topics that occur in a collection of documents. Now, LDA, or latent Dirichlet allocation, is a type of topic modeling, and it's used to classify text in a document to a particular topic. Dirichlet comes from Peter Gustav Lejeune Dirichlet, who was a German mathematician who lived in the 19th century and created most of the statistical logarithmic functions that we use today. We use LDA in order to calculate the likelihood of certain keywords to appear next to each other. So a topic modeling separates a text based on individual topics, individual documents, and then frequency of words. So when we do topic modeling, the algorithm basically reads a document, and then it codes individual words by the number of times they occur, and then it weights these words in a very large document or across a very large size and numbers of documents, and then assigns a likelihood of them occurring right next to each other. So it is trying to understand whether flower, rose, plant, these keywords belong to the same topic because they appear very frequently next to each other. And then it is trying to understand whether company, wage, and employee, these keywords are associated with a different topic. So topic models try to extract themes and topics from a large text database by calculating how frequently or unfrequently certain keywords appear next to each other. When calculating topic models, there are different parameters of how you do it. Now, when we are coding, we're going to use these things. So when you're confused about what we're coding and why we're coding, you can return back to this part of the lecture since it's recorded in order to understand what's happening. So first, the user must specify a value of k. How many different topics do you want to extract from this text? So if we are exploring, let's say, constitutions of 100 countries, we would be interested in looking at how citizenship is defined, how the legal system is defined, how laws are defined. So identity, citizenship, laws, state structure, these would all be topics. So I would say that, I'm interested in finding 8 topics out of this text. So I'm setting the value of k to 8. The value of k, the value of k is basically the number of topics you are interested in extracting from the text. Most of the time, we start with 8, then we try 10, or until we find a meaningful k value, we do some trial and error. So most of the time, in order to find perfect topics in a text, we have to define k value multiple times. Then we have to define a seed value. We use the control argument to pass a random number, which is 1, 2, 3, 2, 2, 2, 2, 3, 1, to seed the assignment of topics to each word in the corpus. We can use the control argument to specify a number of different options as well. So what is a seed? Seed is the starting point for a sequence, and the guarantee that if you start from the same seed, you will get the same sequence of numbers. So when we're dealing with a very large text data set, and when our algorithm is trying to find keywords out of this, we have to make sure that the algorithm that we are running is the exact same algorithm that another researcher would be running on the similar or the same text. So in order to specify how we came up with the topic models, we enter a seed argument in order to understand and express the specific codes in which how we extract our topics. Then we have to deal with a beta value, and the beta value is the likelihood of a term belonging to a topic. So a high beta value means that the keyword that appears in a topic has a very high likelihood of belonging to that topic. If the beta value is low, then it means that probably it belongs to a different topic. So the workflow is usually we have a corpus object, which is a collection of our documents. Then using tidy or tidy texts, which is a package, we convert it into text data format. Or if we are going to do topic modeling, we use quantdata, another text analysis package, and convert this into a document term matrix. So depending on whether I'm trying to build an algorithmic model in order to find topics, or whether I'm trying to do sentiment analysis or text summary or visualizations, I follow different protocols and different packages in order to be able to accomplish that task. Sentiment analysis is, on the other hand, a very different type of text analysis. Now, sentiment analysis gives you the calculation of whether a text is positive, negative, hopeful, hopeless, angry, happy. So in order to do this sentiment analysis, you need a dictionary, or you need a previously coded corpus in order to be able to understand. So let's say in one example, the review says, smells amazing, a perfect purchase, must buy, super amazing. The sentiment analyzer would basically say that this is a positive sentiment indicator because it is working through a dictionary in which you have positive seeds and negative seeds that are previously arranged by programmers. So achieve, advantage, better, creative, efficiency, efficiently, enhance, greater are previously coded as positive, and adverse, against, complaint, concern, damages that are previously already coded as negative. So by using these dictionaries, algorithms can do sentiment analysis, or what we call emotion detection, which is simply just a statistical analysis of the occurrence of negative words or positive words that are previously coded in a text. So this is the main limitation of sentiment analysis. The analysis is only good as the library that is being used for such purposes, which means that if you're going to do sentiment analysis or emotion detection, everything depends on the library through which you are going to do sentiment analysis. So English sentiment analysis is usually easier because English is a very popular language, and you have very large libraries and very large packages that do English sentiment analysis. There are packages such as Vader, Pattern, BERT, TextBlob, SpaCy, Core NLP, Scikit-learn. These are some of the most popular sentiment analysis libraries in English, and they're very accurate. In Turkish or less popular languages, there are fewer people building and maintaining libraries, which is why sentiment detection accuracies are very low. So when you're trying to do Turkish language sentiment analysis, there is one library built by Sabancı and İTÜ, for example, and they have been working on it for several years. There is one attempt at Galatasaray computer science, another attempt at Boğaziçi, but the rate of success are below 80%, which is very, very low. So these are examples of how these Vader, BERT, TextBlob recognizes emotional criteria by example topic sentences. So joy, thanks Blizzard, Mr. Pandaria, 3-day Flip anniversary event extension. So for you to be able to do computational emotion analysis, you need to be more familiar with the libraries that do sentiment analysis. So the text analysis packages that we're going to use for today are TFIDF, which is our own text analysis package aimed at better integration of text analysis tools such as unnesting, tokenization, lemmatization with other tidyverse programs. It is a very good basic package. Text mining package, TM, which is another good basic text analysis package that runs simple commands fast. String R enables string data. What is string data? Text and characters. It enables string data manipulation and find replace tasks very easily. And the topic models package, which introduces statistical commands that enable topic models and LDA. So let's begin with our coding session. Please open your RStudio sessions. Okay, so let's start to code and let's try to understand these things in coding format. Let's create a new R script, which is out fresh. So since there are problems with getting API access from Twitter, we are going to use a previously collected tweet database, and we're going to analyze the tweets of Donald Trump before he was banned from Twitter. So first thing that we're going to do, that we're going to download that Twitter database, and it's already in the GitHub page of Chris Bale. So let's start coding. So let's load a URL. And the URL that we're going to use is going to be with quotation marks. It's going to be HTTPS. What is my slash Chris Bale github.io Trump tweets.r data. This is going to be the data that we're going to import. Let me try to zoom in as well so that you can see my screen better. So when we run this code, it is going to connect to GitHub, and it's going to download Trump tweets.r data onto your environment. So the data is already collected onto your environment with its original object name, which is Trump tweet. And when you click on this, you're going to notice that this is a Twitter data. The screen name is real Donald Trump, which used to be Donald Trump's name before he was banned, his user ID, the date and time formats when it was created, status ID, meaning the unique identifier for these tweets. The most important part, the text of the data. Just met with UN Secretary General Antonio Guterres, who is working on hard, making whatever. So congratulations to our new CIA director. URLs, where it was, how much it was downloaded, how much it was retweeted, favorited. None means not available. External media, TCO. So in data cleaning part of text analysis, you're going to notice that we're going to get rid of this t.co quite frequently. T.co is external link URL. So we usually have to get rid of TCO in data cleaning section. Media type photo, external media URL, expanded URL, mentions user, mentions name. So it's a cleaned format. It's a clean form of Twitter data. For those of you who can get an API, can get tweet data like this, but due to the crisis in which Twitter finds itself, some of you cannot. So we cannot really work with live data because it would be unfair for those of you who can't. So we're working on a same database. So it contains 3,196 observations, which means 3,000 tweets. It's a relatively okay database. And the libraries that we're going to download for now, I'm going to go fast, but since this is a video, you can just stop and slow wherever you want. But for the sake of time, and also since this is recorded, I'm just going to go fast. The first library we have to download is TFIDF. It's already downloaded on my computer, but for those of you who never used TFIDF, you're going to have to do install packages TFIDF. So you have to run this command, and then when you have downloaded TFIDF, you have to run library TFIDF. So I'm now that I have downloaded Tidyverse. So the first thing that we are going to do with Trump tweets is that we are going to tokenize them. What was tokenization? As I mentioned in the lecture, it was breaking down text into its small components of words. So spoke will be a different token. To is going to be a different token. President is going to be a different token. Off is going to be a different token. Mexico. So we need to be able to count them. So to be able to count them, we have to convert them into tokens. So the first thing that we are going to do is that we have to tokenize them using the text of the tweets and created at format, this column. Let's create a new object called tokenized Trump tweets. Where is my smaller sign? Oh, so for I have to do this. Some of you may also have to do this. I'm going to change my keyboard to English because I don't have these arrows. So we have to take Trump tweets and using the pipe function, which you know by now what a pipe function is, we are going to select these as created at and text. Then we are going to connect this by pipe again, and we are going to unnest tokens, meaning we have to tokenize this text. We have to unnest, bring them out of their nests and convert them into numbers according to word and text. This is a very typical format of tokenization. It's how unnest tokens parameter runs. So you're going to notice what happens when I run this command. Oh, so, okay, this is a great learning experience. It says error in Trump tweets. It could not find function pipe. It is because I did not introduce the library which contains the pipe operator. And of course, the pipe operator is included in the tidyverse package. So I have to introduce library tidyverse as well so that we can start using the pipe operators. Okay, so now the pipe operators are included in our session along with a whole bunch of other cool functions. So now I can run this command. So I'm running this command. Now you are going to see that we have a new variable, a new object called tokenize Trump tweets. It only has 2 variables and 81,000 observations. Look how things are tokenized. Every tweet is now separated based on their word and text, and they are listed by created at, which is going to be useful. So one thing that we have to do at this point is that we have to remove stop words. Off, is, a, in, and, is, that. So we have to get rid of all of those. So we can individually get rid of all of those, but most text analysis software, such as TidyText, has a function that already includes main English language stop words to it. So now what we have to do is that we have to introduce these stop words using the data command, and in double quotation marks we have to say stop underscore words. So this is how we introduce this to our session. Instead of specifying each stop word, we can use previously created stop word dictionaries. So now it is here as a promise. Now I'm going to link these stop words to my actual database. So let's create a new variable called Trump tweets top words. And in order to be able to do this, I have to work with this tokenized Trump tweets. I can't do text analysis without tokenizing the keywords. Without counting them, it's impossible to work with them in that way. Tokenized Trump tweets. Now, we are going to use a command called anti-join, which is going to remove everything that goes into the parentheses. So I have stop words. We are going to use anti-join, and once I wrote this anti-join stop words, you're going to notice that now this stop words data contains the actual stop words. Now I'm clicking on this. A's, able, across. So these are all defined as stop words. We're going to remove them from our tokenized Trump tweets. Type operator. Then we are going to count them based on their words, we have to count the occurrence of those words, and we have to see how frequent some words are used. So what we're doing right now is that we are taking tokenized tweets, removing stop words from it, and then we are counting the occurrence of certain words in that. And then we are going to arrange them in a descending fashion according to the number of the occurrence of the words. So I am doing text frequency analysis now. When I run this, we are going to see that there is a Trump tweet upwards new dataset which contains this many observations. And now I still have HTTPS, TCO, AMP, RT. These are stop words that originate from the URLs that we are using. So we also have to get rid of them so that we can start with people, the actual top words. These top words are not really top words, they're just URL links that I need to get rid of. So here, what we do is that first thing, I need a new character, and I'm just writing this here. Type the vertical bar on most keyboards, press Shift and the sideways slash. So you are going to need this vertical bar. It's not I, it's not capital I letter, it's the vertical bar. You need to find how to create this vertical bar on your keyboard. If you need, you can just pause here, look online. If you're using Windows, Mac, or different keyboards, you need to find how to create these vertical bars. So now, what we need to do is that we have to create a new we don't have to create a new object, but we have to change Trump tweet top words by removing those URL links from it. So we are doing exactly the same Trump tweet top words, but in the second one, we are changing certain parameters. So you need an edged bracket here. And what you need is that you have to change and remove all of the following in Trump tweets top words. The first one is HTTPS. This is where you're going to use the vertical bar. T.co, vertical bar. AMP, vertical bar. RT. So you are basically getting rid of HTTPS, TCO, AMP, RT, which are URL. You're basically cleaning your data right now. We are continuing, and we're going to do this on Trump tweet top words and in the word section of Trump tweet top words. So remember, the $sign was for you to change or call a column or a variable in a data object. So what we're doing right now is we're taking Trump tweet top words. We are basically introducing HTTPS, TCO, AMP, RT, and we're doing this in Trump tweet top words, the word column. And in order to finalize this command, I'm going to introduce you a new command called grep, or pattern matcher or substitutor. You're going to write grep, another parenthesis here. Actually, after the grep, you don't need edged brackets, so you need normal parentheses, and then when you are done with Word, you need to add, don't forget this, another comma, because the grep function is going to require another function here. You're going to say that I'm not adding another function by adding this comma. And grep function also takes minus. So when you say minus grep, it means that get rid of this from Trump tweet top words and from their word section. So when you use this, now look at Trump tweet top words. We have 8121 observations. We run this. We are reduced to 7924 observations. And when I click on this, I notice that the URLs are cleaned. We just have regular important words. So one, we clean our data by removing stop words, and then we manually removed URL links from this so that it doesn't mess with our top keywords. So now what we're going to do is that we're going to do top 20, let's say, Trump words. And let's take 20 of the top words in that list. You do that by choosing 1 to 20th of row, and it's going to require column information from me as well. I'm not going to add any columns, so I'm just going to add comma and nothing else, because in trying to call certain row sections or column sections, the first part you need is going to be rows. The second part, you're going to input columns. So I'm not selecting any columns. I'm selecting all columns, but only the first 20 rows. So when I run this, I am now having top 20 Trump words. I click on this. Yes, people, US Democrats, whatever. So this is just basic frequency analysis. Now let's use ggplot to visualize this. Let's bring ggplot. What am I ggplotting? I'm plotting top 20 Trump words. And what are my aesthetic values? The X function is going to be word. The Y function will be the N, meaning how many times they appear. And then let's determine the color fill. We can just say, let's give a different fill color to those graphs based on word. Then we are continuing with a plus sign. Where's my plus sign? Okay. As you remember, ggplot commands usually took plus as end of line separator. We are going to build a bar graph, which is geom bar. The statistics are going to come from each value, which is why I have to add identity. So each value has going to represent a different graph. In this context, let's continue with a minimal theme. You can choose any one you like because these are graphic choices. I'm just saying minimal. Now let's try to run this as it is. Okay, so I have a graph in which let me zoom on this. Different graphs, whatever. Let's put this into an order. For us to be able to put this into an order, we have to add the reorder command, and we insert the reorder command in the X section here. So I'm going to say reorder, parentheses, word, comma, and reorder them by decreasing number of n, meaning reduced n. So it's going to start at the top with people, and then it's going to basically start from the top and go all the way down. But I understand that these are going to basically run into each other. I also want to take these labels and convert them into 90-degree vertical angled text. So I need to change their angles as well. How I do that is I'm continuing after theme minimal. I am going to add in the theme change axis text X. So change the text of the X-axis, such as the elements of the text contains an angle of 90 degrees and horizontal justification, which is how each line should be aligned, at 1, which is at the center. 0 is towards left, 2 is towards right, 1 is right at the center. Maybe we can say, insert a Y label. You can say, for example, number of times words appears in Trump tweets. And maybe in X label, we can write something like top words. So with these changes, let's do another ggplot. Okay, now you are going to see that the graph is ordered in a descending fashion. How each word is represented. So this is basic text frequency analysis. You clean the text, you remove stop words, you remove link texts, and then you count words. When you count words, you come up with the most frequently occurring text. So people, news, president, fake, Trump, country, America, tax, US, time. This is very valuable. I mean, when you analyze this, it can tell you quite a lot in terms of the Trump's preferred themes. So let me maybe say that my first exercise here is text frequency analysis, because now I'm going to do a TFIDF analysis. So my second exercise is TFIDF. Now, how am I going to do TFIDF analysis? Again, it's not that difficult, but we are going to use the TFIDF command in a very with a very small change. So in order to do TFIDF, we need our original data, which is Trump tweets. So it's already downloaded, and the command that downloaded this, what was this? So we don't need to change Trump tweets. We have to continue with that. So the first thing I need is tidy Trump TFIDF. Right. So let's take original Trump tweets. Let's connect them through the pipe function. We need to select this at based on their created at and text, because we're going to connect them again. Then again, we have to unnest their tokens. And how we're going to unnest them will be based on their word. And it is going to be in the column called text. We continue with the type operator. We have to do anti-join stop words. We already have the stop words introduced in our previous session. Then we have to do, sorry, I couldn't do the type operator properly. We need to count the occurrence of words based on their created at. Type operator again. Then basically what we're going to do is that we are going to bind their TF-IDF scores. We have to calculate them automatically. And how it's going to calculate TF-IDF scores will be by looking at word, by looking at created at, and counting the n, the number of occurrence for them. So when I run this command, it is now going to create ID trump TF-IDF. We have a new object. When we click on this, it is going to basically give you word by word, n by n, their term frequency, inverse document frequency, and TF-IDF scores one by one. So as I scroll further, you're going to notice that each usage of the term in Trump's tweets are calculated by their TF-IDF and TF-IDF scores. Now, you're going to see where we're headed with this. Now, we are looking for the keywords that connect, that contain the top TF-IDF values, in which the TF-IDF scores are going to give me the most important keywords in Trump's tweets in specific contexts. So yes, Trump says a lot of people, Trump says a lot of news, Trump says a lot of president, but Trump says this in all of the tweets. Which keywords are frequently used in a small number of tweets? So it's going to give me context-specific keywords that may provide a clearer indication of Trump's broader political agenda. So we need, let's say, top 20 of the most frequently occurring TF-IDF scores. So top TF-IDF is my new object, and top TF-IDF is going to include this, what I did above, the TF-IDF scores. I'm just copying and pasting it here. Then I use the pipe operator in order to arrange them in a descending fashion, so from top to bottom, and the values are going to come from TF-IDF scores. Yes. So now I have these all sorted in this way. And when I say, top TF-IDF scores, and from there, please give me the words, and let's look at, the top TF-IDF words stand for our anthem. Now, this is very, very important. Now, stand for our anthem was a political controversy during Trump's presidency, in which certain African American sports people kneeled during the US anthem. So there was a huge debate between Trump supporters and African American community in the United States. Stand up for our anthem or taking the kneel. So it's a very culture specific, a very context specific keyword that only experts of US politics or Trump politics are aware of. We can maybe say words 1 through 10. Let's see what this gives me. Oops, let me get rid of the comma. Okay, so when I'm asking for the top 10 TFIDF scores, stand for our anthem, CPAC, the Political Action Committee that has been very, very important in Trump's presidency. Karen is a pejorative term used for middle-aged women that in US culture are viewed as very much complaining and maybe entitled. The plumb line EGS collusion, the argument, the keyword that suggests Trump was in contact with the Russian intelligence, Fox and Friends, Easter. So when you do a TF-IDF score, suddenly instead of getting the generic frequency values, which people, news, president, fake, country, tax, time, jobs, this can belong to any other country. So this can be Italian president tweets. It can be Polish president tweets in English. But when you do a TF-IDF score, it gives you contextually important keywords that made a mark in a specific political episode. So this gives you the value, the importance of TF-IDF scores. It gives you context-specific keywords that are almost always more important than just simple keyword analysis or frequency analysis. Now let's move ahead to corpus or dictionary-based approaches. So let's write here dictionary-based text analysis. So let's say I want to create a corpus of words that are related to the economy. I'm interested in whether and how much economy-related words Trump is using. So in order to do that, I'm going to introduce first for example, object called economy corpus. And on this, I'm going to specify my own words in a vector format. So I need C in double parentheses. So what would be some of the keywords related to the economy? Economy would be one of those, comma, unemployment. Make sure you're not miswriting this because it has to match exactly. Trade, of course, is one of those. Tariffs, because Trump used the term tariffs quite extensively in his talks and tweets about China. So this 4 is enough to give you the general idea. So my economy corpus contains 4 words. It is right now here, economy corpus. So in order to continue, I need a new package, which is going to search, find, and extract these keywords. And it is called the string R package. It's already downloaded with me. So I'm just going to say library. If you don't have string R, you do install packages. String R is very useful for text manipulation, character manipulation, find, replace, find, and count operations. So I need to introduce library string R. And after doing that, I am interested in a specific function called string detect. So I am going to basically tell string R to look for these keywords in the wider trump corpus. And I need to move them into a different specific object called, let's say, econ tweets. It's a new object. I'm going to take Trump tweets once again. In brackets, I'm going to use the command called string detect. Then in the string detect, I'm going to basically tell that take Trump tweets, and where is my $sign? So when I say Trump tweets $, it's going to give me every single column, every single variable in there. Here I want the text column, the text variable, and then paste here what I wrote for the economy corpus. And once I do that, collapse the parts that contain, in double quotation marks, the vertical bar that we introduced earlier. And this is important because the string detect argument is now going to find an additional command after the row. So between the last parenthesis and the last bracket right here, enter a comma, because it's going to require a second command. We are not going to use a second command. So we say comma and nothing else. So when I run this, now I have an econ tweets object, which contains 122 observations of 42 variables. Now let's click on this. What does it contain? Great talk with my friend, President. He's doing such a good job. Argentina so transforming his country's economy. Okay, so economy, the keyword has triggered this tweet. Talking trade. Okay, trade. So it has triggered this tweet. Washington Post and CNN have triggered a version of false trade about trade negotiations with China. ZTE, the largest Chinese phone company, buys a big percentage of individual parts of US companies. This also is reflecting a higher, larger trade. Okay, so what you can see is that it is going into the tweet database and finding our economy corpus, and we can change it the way we want. If you like, you can maybe, for the sake of exercise, create a defense corpus and introduce things like defense, maybe Pentagon, or something like that. So play with it. It's really interesting. Dictionary-based text analysis is usually quite fun. Then you can visualize this, or you can say, give me the first few. This is what head means. Give me the first few indicative parts, texts of econ tweets, and give me the text part of econ tweets, and give me 10 of them. When I run this, it is going to give me the first top 10 tweets that contain. So this is a very important and simple way of doing text extraction. Now let's move on to the third element, which is, let's do sentiment. Sentiment analysis. Again, I'm usually skeptical of sentiment analysis because sentiment analysis can only be as good as the dictionary that you're using. With this, we are going to use a dictionary, which is created by a Chinese linguist, which is, if I'm not mistaken, his name was Xi Bing. So we, I think, already have TFIDF. So TFIDF comes with several sentiment analysis software. And one of the sentiment analysis libraries that comes with TFIDF is the Bing Sentiment Dictionary. So when we say head gets underscore sentiments, double quotation marks, Bing, because that's the surname, we are going to get the first 6 values from the Bing database. So two-faced, it's negative, abnormal, negative, abolish, negative. So these are all pre-coded. Bing database contains a very large keyword database that are already coded in a way. So we're going to use the Bing database. It's not perfect, but it's good enough for our purposes. In the future, when you do text analysis, and especially sentiment analysis, you should experiment with multiple dictionaries. So some sentiment dictionaries are good for economics, some sentiment dictionaries are good for policy analysis, some sentiment dictionaries are good for marketing and consumer behavior, for example. You just try and do as much exercise as you can. Let's create a new object called Trump tweet sentiment. So for this, I'm going to require this tokenized Trump tweets. I'm not going to use the whole because I need tokenized the numerical format of Trump tweets. Tokenized Trump tweets. Connect this with pipe. So I'm going to join with the inner join function the sentiment scores that I got from Bing. And then I connect this to, we have to count how many times these sentiments match with tokenized version of Trump's words. We have to count them by created at, and we have to score them based on sentiment, not sentiments, but sentiment. It's important not to use the plural. So now let's run this command. So Trump tweet sentiment. This is a new object. So I am scoring them by date. So in this date's tweet, he has 2 positive, 4 positive, 3 negative, 1 positive. So it's counting how many times the Bing corpus is matching with Trump tweets. That's basically how it calculates and counts the overall sentiment scores. So let's look at head again. Trump tweet sentiment, close parenthesis. Okay, so it's basically just the sample of what we already clicked on. Now I'm interested in how much Trump's negative sentiments increase and decrease through time. So I need a line graph. I'm going to do y-axis, x-axis by time. I want to put this into a line graph format so that I look how it increases and decreases by time. So I'm going to take tokenized Trump tweets, and I'm going to take this. I'm going to create a new variable here, which is going to be called the date. And into this, I need as date function, which is going to create date from the format that I'm going to supply to it. Take tokenized Trump tweets and take the created at variables in that. Now take those created at and then format them according to so I need year, month, date format. So this is how you do it. Year dash, this is a dash, percentage months dash percentage date, and the time is going to be represented as X. So what I'm telling this is essentially this. Take tokenized Trump tweets and look at their created at. So look at tokenized Trump tweets and do created at. And then recognize this as a date format in year, month, date, and time, which is X. Then as date, introduce this as a new column. You're basically creating a new column in tokenized Trump tweets and adding a new variable to it as date. Let's do a run. So now in tokenized Trump tweets, I have three variables, the created at and the date format, which does not contain the time, because I'm interested in exploring this according to just date and not time. So that's why we said X here, meaning that we don't want the time. Don't take into consideration anything else. So now we need to separate negative sentiments as a new object. And for this, we need tokenized Trump tweets. Again, tokenized means counted or countable tweets, in which words are separated into individual words. Again, the inner join format is going to get sentiment scores from the Bing database type function. Now we're going to filter them by sentiment, not sentiments, but sentiment, and only those that equal, we have to use double equal sign here, those that specifically are coded as negative. So what we need is that we need to take positive, positive. We don't want positives. We only want negatives here, only negative sentiment tweets. Then let's count them based on date and sentiment. So this is going to give me the count of each sentiment by date and only those that are negative as defined by the Bing dataset. Now I'm going to run negative sentiments. I have 392 sentiments, negative, negative, negative. These are all Trump tweets. So on this date, he used 8 times negative sentiment. This date, he used 10 times negative sentiment. Cool. Now let's visualize this. We are going to do ggplot. We are going to visualize negative sentiments. The aesthetics are going to come from parentheses. The X is going to come from date, and Y axis is going to come from the number of occurrence of negative sentiments. We continue. We need a line graph, which is why we're going to do G on line. The color in this cortex, yeah, you can do anything you want. You know, I'm just going to say red. Let's see how it looks like. you are going to need size. What should be the thickness of the line that you are working with. So you can do 1, you can do 0.5. I'm just going to say 0.5 just because I'm going to show you that you can use anything. And let's say theme minimal. You can use any other theme that you like, play with it. It's good exercise for ggplot. Let's change the theme in such a way that the axis text of the x-axis elements text, let's say their angles, instead of 90, let's do it diagonally, which is 60 degrees with horizontal justification 1 right in the middle. And size is the font size here. So you can say 12, maybe, play with it. And then we are going to do plot title. We need to title this in such a way. But we are going to do, element text. We're specifying the title. At this rate, it can be horizontal justification 1. Its size should be a little bit larger than the regular text, so the font size is going to be 18. Don't forget the plus. Y label can be in double quotation, negative sentiment tweet frequency, plus sign, X label. What should be X label? So my X labels are dates. Then we continue, and GG titles. We need to specify a title. Here we can say Trump negative sentiment line graph. Run this, and now, so horizontal justification is too much towards the right, so I'm going to do something like 0.5 so that it comes a little bit more leftward. Okay, now it's here, Trump negative sentiment graph. So these angles, 60 is good, but let's do 90 so that they're fully vertical. Okay, they're now vertical. But the size is too big. I'm thinking of 8 size. It's small. Okay. Line color red. Let's change it maybe to blue and run the same thing again. It becomes blue. Size, let's do 2.5. See what that does. It's very meaningless. It's too thick. So it's better to do 0.5 or 0.3, I would say, so that we can see ups and downs much better. So this is Trump negative sentiment line graph. So in every tweet, using the Bing dictionary, it counted the number and occurrence of how many times Trump used negative sentiment. Of course, a US politics expert would look at this graph and would say that, oh, this is a very negative peak because this happened. This, my educated guess, is sometime along the Mueller investigation, in which Trump was being accused of cooperating with the Russian intelligence. And of course, in the run-up to the elections, negative sentiments are more intense. So this is all for today. Next week, I'm going to teach you how to do topic models and latent Dirichlet allocation. But for now, save everything that you did and please upload it on the LMS. You are going to save all. You can say that you can save it as surname, IR421, first project. Please save this in this format as our project. Save everything and then upload it on the LMS. And I'm going to look what you did. So, okay, next week we're going to continue with text analysis by looking at topic modeling. And if we have time, we're going to also include structural topic modeling, which is a more advanced form of topic modeling. So thanks for joining me for today. This was good exercise. I hope you benefited from it. We're going to build on this and go more advanced in the next session. So take care and be well.